All right, so today we're going to work on chapter 19. And then if we do have some time before our quiz, I will start showing you an online free computer program that we will be using for the rest of the course called StatKey. I'll introduce you to it. And then next Tuesday, we'll continue working with it, showing you the different tools that we're going to be using. Okay, so let's get started. Chapter 19. And today, by the way, the quiz will cover chapters 14 and 16. And then there will be a quiz next Tuesday, which will cover chapters 17 and 19. I might have mentioned that this current quiz will be covering chapter 17, and it will not be. I sent you an email about this, but in case you didn't see it. Chapters 17 and 19's quiz will be on Monday. All right. So actually, let's start from the beginning here. I think I started the last time, but then we ran out of time. So I think maybe we should just not go too quickly through this. All right. Let's go through some of these thought questions for chapter 19. Again, chapter 19 is dealing with sampling, the idea of getting samples and applying the results of the samples to the larger population. All right, it says thought question 1, 40% of a large population disagrees with the new law. So think of that, apparently you're supposed to think about the role of the size of the sample. Remember, sample size is the number of people in the sample. All right. So if you randomly select sample 10 people, well, exactly 4 disagree with the law. Would you be surprised if only 2 disagreed or if none of them disagreed? So what do you think? Anybody want to comment on that? Would you expect? Oh, go ahead. Sorry, go ahead.
It's like it seems like 4 would disagree, but I feel like that's wrong.
What?
Maybe.
All right. Don't think about the wrongness of it. Think about you took 10 people, whether you would still get that 40% figure. In other words, would you expect exactly 4 people every time you do it? Would you expect it? Just think in terms of logic, in terms of common sense. Do you think you would always get 4 people who would disagree with the law if you sampled 10 people?
No.
No, of course not, right? It's a silly idea to think that it would always be exactly 4 people, because we're not sampling the whole population, we're sampling only 10 people. So we would expect it would vary, right? Now, maybe it would vary around 4, maybe something, it'd be 2 for some people, some samples of 10. There might be, 6 other samples, 7 for other samples. It is remotely possible that all 10 people would disagree with it, or none of the people would disagree with it. But the point of the matter is it would vary. How about if you sampled 1,000 people? Would you also expect exactly 400?
No.
No. But would you be surprised if you saw 200? And remember, it's 1,000 people this time. Or even none of them disagree. I mean, now we're dealing with 1,000 people. Would it be extremely unlikely if none of them disagreed with the law, or all 1,000 of them disagreed, or even 200 disagreed? Would those be unlikely? Very unlikely?
I think it would be unlikely.
Yeah, it'd be extremely unlikely, because now we're dealing with 1,000 people. We would expect as the sample size goes up, we would expect the proportion of people be closer to that 40%. All right. Think about flipping a coin 10 times. And we want to, and the expectation is we would get 5 heads, but we wouldn't necessarily, right? But if we flip the coin 1,000 times, we might expect the number to be closer to 500, the number of heads. It wouldn't be exactly, But it would be highly unlikely if it was 200 heads or 600 heads or 700 heads out of 1,000. So think of it that way. It's the same idea. So here's the rule. The long run relative frequency interpretation of probability. Remember, the more times we repeat a probability experiment, the closer the result will be to the actual true probability. That's what we're talking about here. You get the idea? And remember the gambler's fallacy. What's the gambler's fallacy say? Well, if the repetitions of the experiment are independent of one another, then you would not expect necessarily that result over the short term. Remember what gamblers do. Gamblers think about long-term probabilities and they apply them to short-term circumstances, and they don't necessarily apply to them if each repetition of the experiment or game, if it's gambling, are independent of one another. Okay, that's the whole key. So sampling works as long as the sample size is large enough. All right, now it doesn't have to be really large. It could be small relative to the size of the population, but it has to be large enough so that you can think with confidence, with pretty good confidence, that you're fairly close to the true population result. Okay, that's the whole idea. Go to thought question 2. The mean weight of all women at a large university is 135 pounds, standard deviation of 10 pounds. Remember, standard deviation is an average spread between different people in the population. All right. Remember, the empirical rule for bell-shaped curve says, talks about what range would we expect for 95% of the women's weights to fall. Anybody remember this? 95%. How many standard deviations from the mean are we for 95%? Anybody remember that?
2.
2. All right. Can you give me a range of possible weights for 95% of the women? Requires you to do a little bit of mental arithmetic here, but you should be able to do it in your head instead of with a calculator. What would be the range of weights for women at a large university for about 95% of all the weights to fall?
115 to 155.
Yes, exactly. 115 to 155. How did you do it?
Well, since 10 pounds is one standard deviation, you just multiply that by 2 and then subtract 20 from 135 and add 20 to 135.
Yep. The 2 standard deviations is 20. 2 times 10. And you subtract it to get the lower end of the interval and add it to get the upper end of the interval. That's exactly what you did. So that's what you would expect. That's an expectation that the range, 95% of the weights in the population would fall between those 2 values. Now, let's say you randomly select 10 women. How close do you think their average weight would be to 135 pounds? If you sampled 1,000 women, would you expect average weight to be closer to 135 pounds than for a sample of only 10 women? Well, you can't really give me at the moment. You give me an estimate, right? At the moment, you can't. You randomly select 10 women. How close do you think their average weight would be to 130 pounds? There is a little formula that we're going to use in a minute to answer that. But do you think if we had 1,000 women, our average weight would be closer to 135 than if the sample was only 10 women? What do you think the answer to that question is? That one you can answer. Remember the idea that the larger the sample size, the closer the relative frequency approach will be to the actual probability. So do you think the average weight would be closer for 1,000 women to the true weight of 135, or do you think it would be not as close as, as for a sample of 10?
It would be closer with the 1,000, like with 1,000.
Yeah, that's exactly it. That's the whole idea of sampling. The larger the sample, the closer you're going to get to the actual average value. All right. So the sample, the average of the sample will be on average, let's put it this way, on average would be closer to the true average of the population than would be a sample size 10. Now, it's possible that for a particular size, sample size 10, you might be closer. But on average, if you did many, many samples of size 10, took the average of all those averages, you should get to be 135. But if you only took one sample size 10, there's a good chance you're not be as close. All right, as a sample of 1,000. Remember, a sample of 1,000, most likely you're going to be a little bit closer. Most likely. All right. So, survey of 1,000 randomly selected individuals has a margin of error of 3%. What does that mean? That means that the results are going to be within 3% of the actual proportion. Suppose 25% of the people believe in reincarnation. If 10 polls are taken, each asking a different random sample of 1,000 adults about belief in reincarnation, would you expect each poll to find exactly 25% of respondents expressing belief in reincarnation? What do you think the answer to that is? So in other words, if 10 of you polled 1,000 adults and asked them, do they believe in reincarnation? Do you think each of the 10 of you would get exactly 25% of your participants saying, yes, I believe in reincarnation? You believe that?
No.
No, of course not. It would vary, right? That's what we call sampling variability. Each sample will give different results, right? If not, into what range would you expect the 10 sample proportions to reasonably fall? And this is where this idea of margin of error comes in. The margin of error gives you sort of the range, all right? When we did that other question just a minute ago with the standard deviation, we came up with a range, all right? So that range is based on what we can call a margin of error, all right? There's going to be some errors in terms of how close those samples are going to be to the true population value. They're going to vary. Some of them are going to be close, some of them are not going to be close. But if we took a range of values, we're going to be pretty confident, all right, that the true population mean is going to be in that range. That's the whole idea, all right? So let's talk a little bit about what we're doing when we take information from a sample and project it or generalize it to the whole population. Now, we work from samples to population, so we're working backwards. Remember, when we took a sample, we took it from the population, right? So we went from the general down to the specific. Now that we have the sample, we're going to be asking the people in the sample some questions or measuring something, whatever we're doing in the research. And then we're going to take the results of the sample and project it back into the population. Get the idea? So we're working sort of backwards from what we were doing before. Before we were going from the population down to the sample, now we're going from the sample back to the population. Okay? So we start with a question about the population, collect a sample from the population, measure a variable or ask a question, all right? And then using statistics, we come up with an answer, and then we want to know how close that answer is to the true population answer, all right? And that's what the whole idea of doing statistics is. Again, samples are going to be the results of different samples would be not exactly the same, all right? Sampling variability. That's what they mean by dissimilarity. It means the samples are not going to give the same results. You could say something like maybe most samples are going to be within 10% of the population answer. You could say that maybe. All right. Again, we're dealing with ranges of possible values. You get the idea? So instead of looking at a particular sample value, we're going to create ranges of values. And then we're going to say with a certain degree of confidence or probability even, we say we're 95% confident that the true population answer is somewhere in between in that range. That's really what we're going to be trying to do. And this is called inference. Inference means applying sample results to the population. So if for example, if we're measuring the average height of people, and let's say the average height is, let me think, let's say of men, we'll just go with men, of 68 inches or something like that. I think that's about right, 68 or 69 inches, average height of men. Suppose in a sample of 100 men, we get, 60, maybe 70 inches. Who knows? Maybe we're getting something larger, or somebody else does a sample of 100 men and they get something smaller, maybe 67 inches. The whole point, though, is that we're going to get different results, okay, from sample to sample. The question is, how close are we going to be with the results that we get to the true population average height for men? That's what we're really trying to determine. All right, so that's what we're going to be doing. All right, now I think we did this last time here. We have a population of, this is an example, using what's called proportions. What's a proportion again? It's a percentage of people with a certain trait, certain characteristic, and it's expressed as a decimal. So a proportion is expressed as a decimal. So we have, let's say, theoretically, we expect 40% of a population to carry a certain gene. Let's say the gene is a bad thing, all right? It's maybe some sort of disease or something. So here's a slice of the population, and the happy face means the person doesn't have the gene, and the X through a box means they do have the gene. Okay, and we would expect throughout the population about 40% of the people that carry the gene. So in the population, we would expect 40% of these little figures here to be with boxes, and 60% with happy faces. All right. Suppose maybe 4 of you decide to sample, maybe through simple random sampling or some other sampling, random sampling, 25 of these people. Each of you sample 25, and then you count the number of people who say they have the gene. Okay, and so one person samples and gets 12 out of 25, which is 48.48 or 48%. Second person does the sampling, gets 9 out of 25, 36%, and so forth. Get the idea? So here are 4 people. Notice that one of them actually got the exact results. That's just a coincidence. It's a coincidence because when you sample, you don't know what your results are going to be, right? You know that you're going to get some answer, but it may not be the exact answer of the population. But here are 4 various results here. Each sample gives a different answer. So again, the whole idea is that the sample results will not necessarily match the population results. And by the way, in real research, we don't know the population proportion. We don't know it. That's why we do sampling, right? If we knew it, why would we bother doing any of this? So normally we don't know the answer to the question about the population, and we want to apply what we get. And again, depending on who you are, you may get one of these 4 results. You notice some of the results are smaller than 40%. Some of them are the same or larger than 40%. All right. So how do we apply it to give an estimate for the true population proportion? All right. So what types of things are we considering or implying when we are doing this type of work? All right, number one, we're assuming that there is an actual population proportion. All right, that's what we're assuming. We're making that assumption. If we're estimating it, we're assuming it exists. All right, or we could repeat an experiment over and over again and get an estimate of it. Okay. Number 2, we can take a random sample, right, and get a large enough sample size that we could actually do the estimate. All right, that's what number 3 is also saying too. So we're doing a random sample, and we want to make sure our sample size is larger. So all of these are necessary to do this estimate. Number one is very important, right? Because we don't have, there isn't such a thing as a fixed proportion out there. Then why are we bothering? Why are we bothering estimating something that doesn't really exist? So this is sort of common sense, I think, what they're saying here. And then they give you examples of different things that we would estimate, like the proportion of voters who favor a certain candidate, or proportion of households who like a certain television program, or proportion of households or people who like a certain soft drink versus another soft drink. Get the idea? That's really what we're doing. All right. Now, again, we're going to be avoiding formulas as much as we can when we're doing this. That's why I'm going to be teaching you how to use this special software program called StatKey. StatKey is going to help us answer these questions without formulas. But it's good to know a little bit about the formulas, just the bare minimum, so that we can make use of them if we need to. So here's a little formula that we may want to use. It's a square root formula here. Suppose we have an estimate, not an estimate, suppose we have an idea of what the true population proportion of people are for a certain trait or for a certain question, like which candidate do you prefer, candidate A or candidate B? So suppose we came up with a proportion of people who liked candidate A. So there's always people on television or in the media who like to guess on that. So suppose we have an estimate of the true population proportion, and we wanted to estimate the standard deviation. So this is the formula that we could use to estimate it. It's a square root formula. Remember, proportions are expressed as decimals, not as percentages. So suppose we estimate that 60% of the population favors candidate A. We want to come up with an estimate of the standard deviation of various people's responses. So this would be a way of estimating it, the standard deviation. You take the square root of a fraction. And what's in the numerator of the fraction? That the estimated true proportion, which is again 0.6 if it's 60%. Then you multiply it by 1 minus that. So 1 minus 0.6 is 0.4. And you divide by the sample size. So if the sample size is 1,000, we would put 1,000 here. If the sample size is 100, we would put 100 here. Taking the square root of that fraction gives us an estimate of the standard deviation. Now we're assuming here that when we use this formula, that the various samples that we could possibly come up with, each one giving a different sample proportion. If we plotted all those on a curve, we would find the curve to be bell-shaped. That's the whole idea. The mean, what would be the mean? Well, the mean would be the estimated true proportion. So we would say that's the mean of that bell-shaped curve, and the standard deviation would be this result, the square root formula. Okay. So just an example here. For example, if you think 40% of voters in the US favor candidate X, and you sample 2,400 people, what sample proportion would be expected to favor candidate X? So what we're doing here is we're saying, all right, we haven't really sampled 2,400 people yet, but suppose we will. We want to know what are the chances that what's the range of possible samples proportions? What would be that range? What would be the range that we would expect? All right. So you plug in 0.4 into this formula, and then 2,400 as the sample size, and then you take the square root of this, you get 0.01. All right. Now, 40% is what you feel is the population proportion, 0.4, converted to a decimal. So we're going to use our empirical rule. Empirical rule says that for a sample of 2,400 people, there's a 68% chance that the sample proportion that we get is going to be somewhere between 39% and 41%. Now, how did we get that? The empirical rule says the mean plus or minus 1 standard deviation. You expect 68% of the results to be in between the mean and plus or minus 1 standard deviation. So 1 standard deviation is 0.01. The mean is 0.4. 0.4 minus 0.01 is 0.39. 0.4 plus 0.01 is 0.41. They're just converting it into percentages here. All right. So don't be confused when they say sample proportion. It's really 0.39 and 0.41, but they're converting it into percentages. Remember, just a few minutes ago, somebody in the class mentioned that 95% of the results should be plus or minus 2 standard deviations from the mean. Again, we would multiply 0.01 times 2 and add and subtract it from 0.4, and we get 38 to 42%. And then almost certain means plus or minus 3 standard deviations, and just know that's what it means, almost certain. Plus or minus 3 standard deviations. 3 standard deviations is 0.03, 3 times 0.01. And we add and subtract this from 0.4, and we get 37 to 43%. So what are these results indicating? The percentage of samples, possible samples, the range of possible samples that we could get if we were going to sample 2,400 people. We would expect almost certainly that this range would be between 37% and 43%. We would expect almost with absolute certainty, almost, not total, 99.7% to be exact. We would expect 95% of these samples to be between 38 and 42%, and we expect 68% of the samples to be between 39 and 41%. All right. Get the idea? So the sample size, this is the whole idea, the sample size influences this square root result, this standard deviation result here. And if you know a little bit about arithmetic, you know that if you have a fraction, you keep the numerator fixed, the larger the number in the denominator, in this case, the larger the sample size, the smaller the overall fraction is. Yeah. Right? It's true, isn't it? You know, 1/2 is a fraction, and if you increase the denominator to 4, it becomes 1/4. That's smaller. That's smaller than 1/2. So the larger the denominator, the smaller this fraction, of course, and then of course the smaller this whole square root would be. And what is smaller here? The standard deviation, the average variability. Okay. So that means if we add and subtract a smaller number, the range will become, or the interval becomes smaller. And that's what we want. We want a smaller range of possible values. Okay. So we want to increase the sample size, if we can, to make that range smaller so that we get closer to the actual value of the population. See what I'm saying? We want our results to be as close as possible to the true population results that we typically don't know. And to do that, one of the biggest things that we can do is increase the sample size. All right, increase the sample size makes that range of values, possible values, smaller. So, and then we feel confident that whatever results we get, personally get, is going to be pretty close to the true population results. All right, that's why sampling works. Sampling works because of this little formula that I'm showing you here. Okay. Again, this is about all the math that you need to know, what I'm showing you here. All right, I'm not going to show you any more because we're going to be using StatKey. StatKey is going to give us these intervals. And when we have these intervals, then we can interpret them. That's the whole idea. We're going to be able to interpret them. All right, what to expect of sample means. Now, we were talking about sample proportions just a minute ago, proportion of people who like candidate A or X or whatever. here we're actually going to measure people's weights, and we're going to come out with average weight. So we're interested in estimating the average weight. Well, in this case here, weight loss. This is a weight loss clinic that's national. Suppose that we have a national weight loss clinic all over the United States. People attend these clinics that last for 10 weeks. Suppose we want to estimate the overall weight loss, average weight loss for everybody who attends these clinics. Now, we might not be able to contact everyone who attends these programs, but we might be able to sample a small portion of those. All right. Says here, unknown to us, population mean weight loss is 8 pounds, standard deviation is 5 pounds. So suppose we are given this information, but it's typically unknown, but suppose we're given the information. The mean weight loss is 8, standard deviation is 5. It says here, if weight losses are approximately bell-shaped, 95% of the individual weight losses will fall between -2 and 18 pounds. Now, how did we get that? Remember, 95% says the mean plus or minus 2 standard deviations. In this case, the standard deviation is 5 pounds. So 2 standard deviations is 2 times 5, 10 pounds. So we subtract 10 from 8 to get -2, and we add 10 to 8 to get 18. So weight loss of -2 actually means you actually gain weight. That would be horrible, right? You attend a weight loss clinic for 10 weeks and you end up gaining weight. So it's possible, according to this, that you could gain weight. And positive 18 pounds lost. Now, what does this range indicate? It indicates that if we took a sample, okay, of people, it's possible that some of the samples would show on average a weight gain, and some of them would show a fairly moderate, close to 18 pounds loss. All right, some of these samples. All right. So we're given a range here of possible results for our samples. That's the whole idea. Suppose you took, let's see, this is samples of size 25, I guess. 3, 6, let me say 9, 12, 15, 18, 21, 24. Yeah. So suppose you took, 4 of you took samples of 25 of these people who went through this weight loss program and asked them how many pounds did you lose? Remember, negatives indicate weight gains. So in sample 1, nobody gained any weight, but there's a couple people who lost 1 pound, and it goes all the way up to 16 pounds. See that? So that would be in sample 1. In sample 2, here's a person who actually gained 2 pounds, that -2, went all the way up to 16 pounds. Sample 3, there was 2 people who gained 4 pounds each, and there's 1 person who gained 18. You get the idea? So these are 4 different samples of 4 of you, for example, sample 25 each. And if we average all those weight losses, for sample 1, the average would be 8.32 pounds was lost. We just averaged the 25, added them up, divided by 25. The standard deviation is 4.74 pounds. So we came up with sample means and sample standard deviations for all 4 samples. Notice that all samples gave a different answer. They are all relatively close to 8. Okay. And remember, the sample standard deviation was 5, and these were fairly close to 5. Right? So the point of the matter is that sampling, even if it's a small sample, 25 each, results are going to be fairly close to the true population average. All right. That's the whole idea. So samples do a good job if the sample size is large enough. All right, so what are the conditions for the rule for sample means? The population is bell-shaped, and a random sample of any size is measured, or we have a population which is not bell-shaped, but we have a large enough sample size. So what does this mean? It means that if the population itself, If we took all the measurements and we graphed it, it would look like a bell-shaped curve. Then we assume any sample will be bell-shaped also. But if the population is not bell-shaped, if it's skewed, remember skewness, left and right skewed, then if we have a large enough random sample, and then we plot all the possible samples of that sample size, then we'll end up with something that will look like a bell-shaped curve. That's the whole idea. All right. So the larger samples, now they see sample size is 30 is considered large, but again, depends on the situation. Any questions so far what I'm saying? I'm trying to show you why samples of certain size will create fairly good estimates if the sample size is large enough. Right? We do random sampling, and we want to make sure we sample enough people, and whatever we're measuring, whether we're measuring a proportion or a mean, the results should be pretty close to the actual population proportion or mean. And we use ranges of values to estimate how close we are. That's really what I'm talking about. All right. Okay. So now one of the things that we have to make sure, this is very important, that if we draw the sample from a population, we want to make sure that when we interpret the results and apply it to the population, we apply it to the correct population. It has to be to the population from which we drew the sample. For example, if we were finding the, let me think of it, Rowan students. Let's talk about Rowan students. Suppose the population is Rowan students, and we were measuring the average GPA of Rowan students, and we took a sample of Rowan students and calculate their average GPA. And then we wanted to say something about how it was estimating the population GPA. You can only apply it to Rowan students. You can't apply it to any other university. All right? Why? Because the population is Rowan students. It's not all universities. So be very careful not to apply the results to a larger or different population. That's a big mistake some people do make. All right. So we have to think about which population are we drawing the sample from? And that is the only population from which we can make an interpretation. We can't make an interpretation to other possible populations. All right. Only to the population from which we took the sample. All right? And that's what they're showing here. They're showing what, they're asking what's the actual population here. So a weight loss clinic. All right. So what is the population? Current and potential clients of the weight loss clinic. All right. That particular weight loss clinic. It's not all weight loss clinics or all weight loss programs. All right. If we were interested in average age for when left-handed adults die, the population is left-handed adults. We can't apply it to all people who are right-handed. We can't apply it to right-handed people. Okay, so we have to think about what is the population, and that's where we can make that interpretation, not to any other population. I know I'm repeating myself, but it's extremely important. All right. Now, if you remember, we had a square root formula before for population proportions, right? We came up with a standard deviation of a population proportion. Here, this is the formula for a standard deviation. Notice what we do is we take the population standard deviation and divide it by the square root of the sample size in this case here. And this gives us the standard deviation for a bell-shaped curve, where the bell-shaped curve is we'll list all the averages, all the possible samples that we could draw from that population. So what is the mean? The mean is the average of all those averages, right? The mean. And the standard deviation would be the population standard deviation divided by the square root of sample size. Now, how does that work? Let me just show you an example of this. We have about 5 minutes left. So, by the way, we're not going to get to stat key today. We'll get to it on next Tuesday. All right, so how does this work? So suppose we are estimating that the population mean is 8 pounds and the population standard deviation is 5 pounds for people who are in this weight loss program. Suppose we take samples of size 25. Suppose all of you do samples of size 25. You're all going to get different answers for the mean, right? The average for your samples. If we were going to plot all of your sample averages, if there were enough of you, we would end up with this bell-shaped curve, where the mean would be the average of all of your sample averages. So if you took the average of all the sample averages, it would be a very good estimate for the population mean. And actually, if you had all the possible samples, it would be the average. So the average of all these samples averages would be 8. And the standard deviation of all these sample averages would be 5, the population standard deviation, divided by the square root of the sample size 25. And that comes out to 1 pound. And then you can make this determination. You could say, all right, of all the possible samples that we could get sample means for this weight loss program, all the possible samples of size 25, we would expect 68% of those samples to have sample means between 7 and 9 pounds. We'd expect 95% of these samples to have sample means between 6 and 10 pounds. And we almost certainly, 99.7% certain, that the sample means will be between 5 and 11 pounds. And how did they come up with this? Again, 68% is plus or minus 1 standard deviation. So 8 minus 1 is 7, 8 plus 1 is 9. 95% is 2 standard deviations. 2 times 1 is 1. 2 times 1 is 2. 8 minus 2 is 6. 8 plus 2 is 10. And again, almost certain means plus or minus 3 standard deviations. 8 minus 3 is 5. 8 plus 3 is 11. That's how they came up with this. Okay? And this is giving you an idea that if the sample size is large enough, okay, the sample size is large enough, we can estimate where the various samples values would be. Relative to what? Relative to the true sample mean, the true population mean. All right. So that's why sampling again works. We can come up with these range of possible sample means. And then they show you the example here in case we increase the sample size to 100. Notice in this case, the standard deviation is 0.5 because the sample size is larger. So that means these estimates is plus or minus 0.5 for 68%, plus or minus 1 for 95%, and plus or minus 1.5 for 99.7%. All right. And the rest of this, now this here is, let me just tell you, we have 1 minute left. This slide right here, number 21, tells us what we're going to do for the rest of the course. We're going to do 2 things. We're going to create what are called confidence intervals, where we can say something like we're 95% confident the true population mean is in between 2 values, something like that. And then we're going to do hypothesis testing, which basically says we're going to hypothesize what the true population mean or proportion is, and then we're going to use the data from the sample to prove or disprove whether that hypothesis is true. That's what we're going to do for the rest of the course. And both of these are called inference. I'm going to take information about our sample, project it into population. All right, so that's it for this chapter here. We do have a quiz now that we're going to be taking. Should it be open right now? Give me a thumbs up if you see it. So you may begin this not begin the sample, begin the quiz. And again, we'll be having another quiz next Tuesday, all right, which will cover chapters 17 and 19. Make sure you read the chapters also. All right, go ahead, and we'll see you later.